This is David Spears, Civil Engineering Instructor at Texas Tech University, talking about CE 2301 statics. We're going to do a truss member forces by the method of sections for this problem. We've got a triangular shaped sort of vertical truss as shown there on the left, and it's got those loads 4 and 8 kilonewtons with those points shown. And the goal of this is to find the member forces in members BC, BG, and GH. So we want to find a section with the method of sections that we can cut, and cut no more than 3 members. And so coincidentally that just happens to be right there, which cuts the 3 members that we want to know the forces in. As all these truss problems involve a lot of geometry, first we need to look at what's happening with the slopes of some of these sloping members, especially BC and BG, that we need to analyze. So we need to develop sort of a Cartesian form coordinate system, and we can analyze those slopes, and then we can plug them into the equations that we need to use. So I've drawn a little similar, it's really a similar triangle issue. If we have 4 vertical steps that add up to 30 feet, 4 times 7.5 meters on here on the left, then we've really got a total of 30 meters tall. And down at the base you see it's from A to I is 16 meters. So we have a triangle that looks like this. It's 30 vertical, 16 horizontal. Square root of the sum of the squares gives us the hypotenuse of 34. And we'll talk about that in a second. It's really an 8, 15, 17 relationship for the slope. But now we also want to see what each one of those horizontal steps is. And so one way of looking at the similar triangle problem is to say, well, the vertical is divided into 4 units. So 30 is 7.5 meters times 4. Therefore, 16 has got to be x times 4. Same number of increments. So we can quickly solve for x is equal to 16 divided by 4, or 4 meters. So at the top we have this x, which is 4 meters, 2x, 8 meters, 3x, 12 meters, and 4x, 16 meters at the bottom. So that's sort of the xy, the Cartesian components of that truss. And so we can observe that this outside line, this line is really a 30 to 16 to 34 slope, or really dividing everything by 2, we get 8, 15, 17 for that outside line, which ED all the way down to AB, including CB, are that slope relationship, 8, 15, 17. Now we've also got a member that's sloping, that's a different geometry. It's member BG. So looking over here, that's one we want to focus on. What's the slope of that member? And from the similar triangles we say, well, from C to G is 8 meters, and from B to H is 12 meters. Well, we're just looking at BG on a Cartesian coordinate system. It's going over 12 in the x direction and up 7.5. So BG is a 12 in the horizontal, and let me erase that line, and a 7.5 in the vertical. I can observe there a common denominator of 1.5, divide everything by 1.5, and I'll translate it over here to my section of the truss that I'm going to analyze in a minute here. So, as I say, we've got a cut right here, BC, BG, and GH. And so we have our choice of analyzing either the top half or the top part and the bottom part. Well, the bottom part involves these reactions at A and I, and I don't really want to mess with those if I don't have to. So I'm going to analyze the top part of the truss. Each one of them is a rigid body that it's in equilibrium, and the sum of the forces and the sum of the moments on everything has got to be 0. So I always want an engineer to be an efficient engineer and analyze the easy part. So that's the top part of this truss. So over here I have just the top part, section cut through there, where I noted it on the drawing on the left. So I've got these 3 member forces that I am going to want to solve for: BC, BG, and GH. And I only need to consider these 3 forces, 4 kilonewtons, 8 kilonewtons, and 8 kilonewtons, because that's all that's acting on that section of the truss. The whole thing's got to be in equilibrium, and these 3 member forces, BC, BG, and GH, keep it in equilibrium. So now I just need the geometry of these members. So BC, we said, is just like that outside line of the entire truss. It's an 8, 15, 17. So I've got an 8 and a 15 and a 17. BG is the 7.5, 12 thing. I divide both those numbers by 1.5, and I get an 8 horizontal to 5, which makes the hypotenuse of that the square root of 89. So that's the slope relationship of BG. Now I'm all set up. I know the components of everything, and I just need to start solving. The first one I'm going to solve is BC. So I'll do that in green here. To solve for BC, this member right here, I really want to sum moments about a point that intersects the other 2 members. And that, of course, is this point G. And so I want to sum moments about G. Everything's got to be in equilibrium. Sum of moments about any point is 0. Counterclockwise is positive. Starting up at the top, I've got 4 kilonewtons. It's trying to rotate clockwise, so it's -4. Negative for the rotation, 4 for the force, and it's a distance of 15 meters above it. Then I've got the 8 kilonewtons, and that is also trying to rotate clockwise, so it's a -8 times 7.5. Then BG and GH are eliminated because they intersect that point, as does that other 8 kilonewton force. So all I need to consider is the force in BC. Well, if I draw the little components of it, this is 8 17ths, of BC. Well, it intersects point G also, so I don't have to worry about it. The only one I need to worry about is this vertical 15 17ths BC force. So it is, from the geometry of the truss, this distance is 8 meters. So it's trying to rotate counterclockwise, so it creates a positive moment. And its force is 15 17ths of the total force in BC. That's the force. The distance is at 8 meters, horizontal. So I can rearrange that. These 2 numbers that I know the numbers are total up to be -120. And so BC is just rearranging +120 times 8 times 15, times 17 divided by 8 times 15. Do the math, and that works out to be 17.0 kilonewtons. The positive means it's the direction I assumed it, which is tension. And I did forget to mention that I always assume positive on these unknown number forces. Okay, I've got BC. Next I want to try to get BG. And once again I want to find a point that what I want to do is get, BG. So I want to find a point. If I can, I like sum of moments because then I can check with sum of forces at the end. Find a point that both BC and GH intersect. Well, that's out here at point E. the tip of the truss, the top of the truss. And that eliminates some other forces, so it's really a good point to choose. Let me draw in the components of BG. At point G, I've got down 5 over the square root of 89 BG. And then horizontally, I have 8 over the square root of 89 BG. Getting that from my slope diagram. Now the sum of the moments about point E is equal to 0. Therefore, I've got the 4 kilonewtons up at the top intersects E, so I don't have to consider it. So I just have these two 8 kilonewtons, and they're trying to rotate counterclockwise, so they're positive. So I have 8 times 15 for the bottom one. That's 2 times 7.5. And then the one right below it is only 7.5 away. Still positive rotation, plus, so 8 times 7.5. Then if I look at GH, well, even the vertical part of GH, because it acts at point G, of BG, excuse me, intersects, this 5 squared of 89 BG intersects point E, so I can eliminate it also. So this is like wonderful. So the only one that creates moment is this horizontal part, the 8 over the square root of 89. It's trying to rotate clockwise, so it's negative. The force is 8 over the square root of 89 BG. That's the force. The distance is also 2 times 7.5, or 15 meters. Okay, these two things, 8 times 15 and 8 times 7.5, add up to be 180, positive. Rearranging that, I can say that BG, which is negative here, and this, taking it to the other side of the equal sign, is positive 180 times the square root of 89 divided by 8 times 15. Again, which is going to be equal to 14.15, once again positive, so it's tension, 14.15 kilonewtons, positive means it's tension. Finally, I've got the force in GH, and I could use sum of forces, but I'm saving it for the last as a check. So let's sum moments about this point that's off of the section, but I can still sum moments about it. Connect those 2 points, BC and BG, where they intersect. They intersect, looking at my truss, at point B. So I want to sum moments about point B, which, like I say, is actually off the truss, but it doesn't make any difference. It's still a point in space that I can sum moments about, and it eliminates a lot of unknowns. So I have sum of moments about point B is equal to 0, and that's equal to, I have to consider all 3 of those external forces. They're all trying to create clockwise rotation, so they're all negative. Negative 4 times 3 times 7.5, or 22.5, minus 8 times 15, minus 8 times 7.5. Then I got to look at what GH is doing. It's also trying to rotate clockwise, so it's negative GH. And if I go down here all the way to where horizontal distance from GH to that point B is that third point in my similar triangles, 3x, which is 12 meters. So this distance is 12 meters. Do all the math, combine all 3 of these known forces, and I get negative 270 minus GH times 12. Therefore, GH is going to be negative. GH equals negative 270 divided by 12, which is equal to negative 22.5 kilonewtons. The negative means it's the opposite of what I assumed. It's compression. So that's the solution. But if I'm on a test and I want to make sure that I've got everything right, always want to check my work if I have time, and I can do that with the sum of the forces. So I can check with the sum of the forces in the x direction, and adding them all up, positive is going to be to the right. I have 4 plus 8 plus 8, the external forces, minus 8/17 of BC, which I found out was positive 17.0, and then also minus 8 over the square root of 89 times the force in BG, which was 14.15. Both of those are to the left. And do all the math. This works out to be 8, and this is 12. So I have 20 minus 20, so that does in fact equal to 0. It's checked. I can check the force in GH also with the sum of the forces in the y direction. And that's equal to, all I have is those y forces in BC. Oh, and I forgot to. I should have gone up here. Once I found that GH was negative, I should have reversed that arrow. So I want to do that right now. GH is 22.5. And it's going up instead of the down that I assumed by assuming tension. Anyway, just looking at my drawing, I have negative 15/17. That looks like a positive. Negative 15/17, the force in BC, which was 17. Also negative 5 over the square root of 89 times the force in BG, which was 14.15, plus that 22.5. These work out to be negative 15 and negative 7.5, plus the 22.5 does equal to 0, so that one checks also.